In this example, we will discuss more about the kinematics of 3D rotations. This system consists of a gear spinning around its axis at constant angular velocity, and at the same time it's rotating about central shaft at constant angular velocity. Let's first have a look at the trajectory of the small ring motion. We can see that the ring changes its direction at every instant, which means its velocity will change instantly during its motion, and also its acceleration. Observing the system from top view, we can see that it's spinning at 20 rads per second. Notice that we cannot decide if it's rotating clockwise or counterclockwise, as we can see both cases during the rotation. So we need to locate the position of the ring when calculating its velocity so we can decide the sign of omega. Now looking from the side view, we see that the shaft rotates at constant angular velocity of 10 rads per second. And from this side view, we can decide that it's rotating clockwise. A good point to start is to set up an appropriate 3D coordinates so we can clearly read all vector quantities and decide our zero velocity point, and make it more easier to locate the ring at any moment and build its position vector. And for this problem, we are going to find the velocity and acceleration of the ring at the moment it makes 30 degrees angle with the positive y-axis. Now we build the omega vector, and notice there is no rotation around the y-axis. Then we have the linear velocity equation of the ring. We then build the position vector of the ring at this moment. By starting from the origin of our reference coordinates, we draw the vectors heading toward the ring. Remember that position vector must have only x, y and z components, which means any angled vector must be transformed to its rectangular components. Since the center of the reference coordinates is the zero velocity point, as it does not move at all, then we can refer the velocity of the ring to this point. Now applying all the values in the equation, and doing the cross product, we can finally find the linear velocity vector of the ring at this exact moment. Now working on the acceleration. First we choose the reference rotation of the coordinates, and it will be the rotation of the whole system around the x-axis. Now we find the angular acceleration alpha. Notice that omega dot is equal to 0 as all omega components are constant values and not changing over time. Now we apply all the found values in the equation of linear acceleration. Notice that we can replace the term omega cross r by its equivalent velocity vector. And this is a good step as we minimize the calculations since we already found the value of v. The idea of this example is to help you be able to track the rotation of objects, especially if the rotation takes place around more than one axis at the same time. and also to help you realize that even if the whole system rotates with constant angular velocities, it does not mean that there is no angular acceleration. And this acceleration rises from the fact that the reference frame itself is not fixed. Thank you for watching.